Okay, so we're going to be doing binary search, and we're going to be looking at the way that you do a code analysis for this one because it's a bit more complicated. So first pause the video, and I recommend you just, try to get an understanding. So first try to just try an example list. So it's going to be a sorted list. So on a pencil, with a pencil and a piece of paper, just see if you can understand how it would sort a list like this. And then when you're ready, you can come back. Okay, so welcome back. So let's just do a quick example of how this code works. So you have a list, and let's say this is the input list. 1, 2, 3, 4, 5. Perfect. Okay, so I is going to be 0. So I is going to point at this because this is the index, right? Yeah, it's the same actually because I started at 0. That makes it easy. And j is going to be the length of the list. So j is going to be pointing at this right there. Okay, so we have while I is smaller than j. Okay, and then we're going to set the midpoint to be I plus j's half. So this is going to point to the middle. Alright? And then, so first of all, in this condition, so let's say let's give an example here, binary search. Then let's call this list A. This is the list, and then say what we're looking for is 3. Then the first if condition is if mid equals 3, and return true. So in this case, we know it happens. Now let's say that we're looking for 5 instead, so that we can see what other conditions happen. So we have else if okay, so then we look at the mid, the value of the middle. So let's see here, L mid. So this will point to that. The value in the middle is smaller than x, then I equals mid plus 1. And so if this is the case, so let's so right now the value is x is 5, right? X is 5, and this value here is 3. So this is smaller. So what would happen is I equals the mid being 3 plus 1. So now I is going to be equal to 4. Which means that I now points there. And you can kind of see essentially, it checks for the middle and it cuts the list in half. And now it's only looking at this part. And the same thing, if say we were looking for a value that's smaller than 3, so like 2, this is 2, then j equals the mid minus 1, and the mid is 3, so this one is 2. So then now the range is here. So as you can see, it kind of it looks in the middle, and then it checks the what values are greater, and then it goes left or right. So each time it iterates, if it doesn't find, for each loop it iterates, if it doesn't find anything, then the amount that it needs to check is cut in half. So that's that's essentially what it is. And there's some, I'm not 100% sure about whether this would choose 2 in this situation or 3, but it doesn't really matter. This is the general idea of it. Okay, so then let's copy this, and then let's start refresh here. Okay, so we have that there. Hopefully you'll be able to understand how the code works. So first we're going to be setting, in order to figure out exactly how this works, we're going to be setting, we're going to say let r equals to j minus I. Okay, so j being this minus this. So this question is asking what's the initial value. So initially j equals n and I equals 0. So r equals n. Okay, so for what values will r terminate? So let's think about this here. So the program we know from here runs as long as this is true. So it terminates when and we just flip this, right? So this terminates when I is larger than or equal to j. I is larger than or equal to j. Which means that, and if, like, so consider if I is equal to j, then r equals to 0. Consider if I is larger than j, then r is smaller than 0. So then we know that the value we're looking for is smaller than or equal to 0. Will terminate. Okay. Alright, so then let's just take this whole thing. Whoops. Alright. So let's take this whole thing and move it over here so that we can still see it. Okay, so now we're saying that, okay, so we know that it decreases by a factor of 2, and if we say rk be values of r immediately before kth iteration, and we let rk1 be the values of r immediately after kth iteration, then okay, so since we know it decreases from a factor of 2, let's think about rk being some iteration. What do we know about rk plus 1? Well, we know that after this iteration, this one, the value that this one has is going to be, half. So we know that, first of all, that that this value is going to be larger, right? And we don't know by how much, but know that value is larger. Let me just erase this here. This is really the most complicated part of this whole thing. So this one's going to be larger than this one, but by how much? Well, we know, or we consider another way, 1/2. If we multiply this by 1/2, then it's going to be roughly equal to, this. It could go lower, right? And so we change this then to a larger than or equal to, which is basically saying that the relationship between rk plus 1 is that at most it's going to be 1/2 of rk. That makes sense. It's something to kind of wrap your head around and get used to, I know, but if you really have to convince yourself of this, then it's a good idea to pause and think about this some more, because this is the main, if this is a exam question or test question, this would be the main thing that we need to figure out. So assuming that you understand or at least accept this conclusion, then we want to prove this. Okay, so then to prove this, okay, let me take a look at what I did here. Okay, so prove this, we first declare a couple variables. So let ik, jk, since we before, I'll write this again, it's going to be j minus 1. So we want the I and j values for the kth, after the kth iteration, and then we also want the same thing after the kth iteration. So be the values I, j immediately before and after kth iteration. Okay, so that we have that set up. Then we know this. Okay, we know that rk equals to jk minus ik, and our k plus 1 equals to jk plus 1 minus ik plus 1, right? And then we consider, okay, so we look at the code now, what we want to prove. And there's, other than this thing here, which we're going to ignore, there's two possibilities. One that I changes and one that j changes. So we're going to consider this in cases. So, we write, since there are two possibilities, we consider them by cases. Okay, so case 1, and we'll just divide this right down there. Case 1. Now, case 1, we assume that I stays the same and j changes. Alright, so if I stays the same, that means that ik plus 1 equals to ik. But j k plus 1 equals to, and then we consider what exactly the code does. So the code takes I and j, right? Takes the values of I and j and it divides it by 2. And we're going to be saying the I and j of the kth iteration. And then we're just going to put a floor there. It could also be a ceiling, and I don't think it would change anything. And this is going to be, and we're going to subtract that by 1, because if we take a look at the code, so first we consider this one. So it's the mid. The mid is going to be these two multiplied by 2, subtracted by 1, right? Okay. So we want to calculate what rk plus 1 is. And we want to eventually find that rk plus 1 is larger than or equal to half of rk. Okay, so we know this is true. Okay, now we replace this over here. And then we know that ik plus 1 is equal to ik, so we just write ik there. Okay, so let's move this part inside. So we know that we can do that since, you know, it doesn't really change anything with the floor. Okay, and then we break up these fractions and we move this inside, and then we want common denominator, so we multiply by 2 and divide by 2 there. Okay, and then this is equal to j of k minus I of k, because you have 2 minus 1, divided by 2. Or rather, we can rewrite this as times 1 over 2 to the floor minus 1. We know that this equals to r to the k. So r to the k minus 1. Okay, and for what we actually want to prove is that this is larger than this value here. We want to find this value here smaller than or equal to rk plus 2. Well, we know that this is going to be smaller than or equal to rk, not plus 2, times 1/2. Since, you know, you're subtracting by 1 there. So that's one side. And in case 2, j stays the same and I changes. Okay, so then j stays the same, then same thing, equals jk, and then ik plus 1, and then we consider the code. So now we're considering this. So we have j plus I divided by 2 plus 1. So ik plus jk divided by 2 floor, and we're adding 1. Okay. And then we consider rk plus 1 equals to what? And then we have jk, since, you know, or rather, or let me write this out. Ik plus 1. Okay, so then we have jk minus, and then we have the floor ik plus jk divided by 2 plus 1. Right. And then we want to move jk inside here, and since this is a negative, you end up multiplying a negative, so then we just write ik, and once again we split up the fraction, so this is the original from here, and now we subtract since we're moving it into a negative, so jk, and this is 2 over 2. Cool. Alright. Then you end up with ik over 2 plus, or rather, minus jk over 2 plus 1. And then we do this thing where we change it into a ceiling, and we make this into jk minus ik over 2. And we know this because the negative of a, there's a negative here, negative of a floor equals to the ceiling of the negative x. Okay, so that has a negative, this one doesn't, which is equal to the ceiling of 1/2 times rk plus 1. Right. And actually, well, since this is actually being subtracted, this would become a negative. Okay, so then we know that this is smaller than or equal to 1/2 times r to the k, and that's it.